Hello, my name is Sienna Rodriguez, and I'm currently completing an independent research project with Dr. Kidan Hutt at Eastern Connecticut State University. Our research is focused on identifying a systematic novel psychoactive stimulant classification based on chemical structure and bioactivity, and then building a representative library to be used in identifying never before seen substances through the use of molecular fingerprinting. So NPS are technically considered legal highs because they circumvent the drug abuse legislation. So basically, underground scientists make slight modifications to the illegal drug's chemical structure, technically making a legal and unregulated derivative of the illegal drug. And then, so our main concern with NPS is that they have similar structures that produce similar psychoactive effects to traditional illegal drugs like cocaine, cannabis, and ecstasy. And then these compounds are intentionally mislabeled and then sold online on the black market. The main mechanism of NPS specifically for stimulants are monoamine reuptake transporter inhibition and or release facilitation. The inhibition of dopamine and noradrenaline reuptake results in the overstimulation of the sympathetic nervous system, and it actually is the cause of those psychostimulatory effects the person exhibits after taking these drugs. So right now there's a technique called Raman spectroscopy that is used to identify drugs by what's called a spectrum fingerprint, and this device contains a software that's installed within it, which acts as a library database and is used as a reference when comparing the spectrum fingerprint of a known and a unknown substance. And then a probability is then calculated to show how closely those two substances are. And the goal of our project is to contribute to the advancement of chemical analysis regarding Raman spectroscopy and designing an accurate, concise, and representative library. The current database library was analyzed, when analyzed, is not efficient because of the alarming increase in new NPS, and it simply just isn't able to keep up with the amount of new NPS that's entering the black market. So the pharmacological profile refers to the specific fingerprint created when experimental assays of NPS against multiple protein targets in the CNS. We are also concerned with the structured molecular descriptor, which refers to the in silico computed fingerprint. It also is important for me to emphasize that we're using unsupervised and supervised machine learning to conduct a clustering analysis that will allow us to create a representative library to improve the accuracy of chemical identification. Molecules with structural similarities typically share the same pharmacological activity. So using algorithms, binary fingerprints were created to translate the shape and structural features of a molecule into a language a computer can interpret. And then we created unique molecular fingerprints for the various drugs. And we were able to use machine recognizable methods to quantitatively describe molecular structures by using different molecular fingerprints such as PubChem, Morgan, RDK, and MACCS. We intentionally were looking to see if the molecule contained specific structures of interest, and if it did, it was given a 1, and if it was absent, it was labeled a 0, and then from this labeling, a substructure fingerprint was created for that particular molecule. And different molecular fingerprints were used to yield a Tanimoto coefficient to identify how closely related the drugs were. A Tanimoto coefficient ranges between 0 and 1, where a number closer to 1 indicates more similarity. And then in this study, we first conducted a unsupervised clustering analysis where we tested 4 different molecular fingerprints to see which was most accurate when creating a representative structure for stimulants and hallucinogens. And this analysis was also done to see how similar these drugs were from a structural and pharmacological perspective. With the sample, we then used some criteria to evaluate the dissimilarity between the compounds, and then we used the distance matrices to connect the dots and then merge it into a large tree. And then the branches were separated into different clusters using the 4 fingerprints fingerprint methods to see the cluster results, just to see how they were correlated with one another. We also established the data mining approach by using a classification model to virtually screen and identify new NPS with high abuse potential. So a high throughput bioassay screening data of various targets were collected from PubChem, and then their reported IC50 values were analyzed and then used to label each tested compound as either inactive or active inhibitors against the target. The various substructure fingerprints were used as the molecular descriptor. And then in order for us to kind of test this model, we first used 80% of the data inputted to train the model to identify whether the substance was active or inactive. And then 20% of the data was used to actually test the performance of the model. The second test set was generated using the NPS data set. So the test set used the RDK fingerprint, which had an average MCC score of above 0.75 for all targets, which indicated excellent performance of the trained classification models using support vector machine. And due to the difference in compound distribution and limitation from the PubChem screening dataset, the performance was in general worse when evaluated with the NPS set, but the RDK fingerprint still produced the best performance for all targets except CERT and D2. So thank you so much for listening to my talk, and I hope you have a great rest of your day.